So the video will be recorded, the messages will be recorded, so you can look back on this. So questions, you can either ask it in the text on the side in the chat box, or you can ask it, just turn on your microphone and ask a question, it'll come through. So you can ask questions, the homework, the classwork, the assignment on the College Board website, the take-home test. How is April 3rd looking like for a return? So the district pretty much has been saying we'll reevaluate by then. Honestly, with the trainings and things they've been sending out, it makes it sound like they're saying like, oh, week 1, 2, and 3, which is the ones we're scheduled to be off, and then they are already talking about a week 4 at home. The CDC has said something about 8 weeks, and it seems like, if anything, this is spreading further. So no official word on that, but I kind of have a suspicion that it'll be a little bit longer. So how often will we be meeting online? So my plan right now is every other day, similar to how we have a class. So probably similar, like A, B, A, B, A, B days. So I'll probably do my first class. I'll probably do it actually Monday for you, because AP, you're on a little bit more of a time crunch than my other classes. But then after that, it'll go back to you having 3 classes, then 2 classes, then 3 each week. Every other day, I'm going to do a tutorial. So next Monday, I'm planning on having an actual class again. And then Tuesday in the afternoon, I'll have a tutorial. So I'll try to post that a little bit more officially. So trying to start this around 10 each morning, and then probably around 1 or 2 would be the afternoon tutorials. If you have any other questions, you don't necessarily have to meet online. I have been checking my email a lot more, and even outside of work hours. So if you send me an email, I can do that. If you're really struggling and you send a request, as long as I'm not in the middle of something else, I could try to do another Google Meet to work through something real fast if it's a real quick thing. But yeah, things like that. So 205 is what you want me to do. And I like this new setup because I'm using my gaming computer now, so everything is really fast. I don't have to worry about my 8-year-old laptop. 205. All right. That's not fully on the screen. All right, a 15 kilogram mass moving at 8 meters per second collides elastically with a 5 kilogram mass at rest. What is the speed of the 15 kilogram mass after the collision? All right, so when we're talking about elastic collision, all right, so an elastic collision, what's being conserved in an elastic collision? Energy, and then also, if there's no friction, what else has been conserved? Energy and momentum. All right, so we have conservation of energy and conservation of momentum. Anytime they don't give us any information about either mass after the collision, we're probably going to have to use conservation of energy and momentum. I'm going to start off looking at just conservation of momentum. So total momentum before the collision, mass 1, v1, mass 2 times velocity 2 initial is going to equal total momentum after the collision. Is that kind of clear enough? Or is that hard to see? I can try to write a little bit bigger than that. All right, so momentum is conserved. So let's call mass 1 the 15 kilogram mass. So 15 kilograms moving at a speed of 8 meters per second. The other mass begins at rest. And then I don't know anything about the other two masses after the collision. So it's just going to be have 15 times the final speed of object 1 plus 5 times the final speed of object 2. And so we're kind of stuck here. 8 times 15, what is that, 120? Yeah, 120. 120 is equal to 15 times V1 final plus 5 times V2 final. So now we're kind of stuck with two unknowns to where we're going to have to use conservation of energy, and in particular on a flat surface, conservation of kinetic energy. So elastic, therefore the kinetic energy before 1/2 mass 1 initial speed of mass 1 squared plus 1/2 mass 2 initial speed of mass 2 squared. It's all equal to 1/2 mass 1 final speed of mass 1 squared plus 1/2 mass 2 final speed of mass 2 squared. So I can divide out the 1/2. I can substitute in some values. So mass 1, 15. Speed 1 is 8. I have to square that. The second mass begins at rest. Then I have 15 times speed 1 final squared plus 5 times speed 2.
Sorry.
That's all right. Yeah, and if you ask a question, you can ask me to mute it first, and then there'll be less feedback. All right, so we're probably going to have to square something here. So we're going to have to square a polynomial. 15 times 64 is 960. Final squared plus 5v2 final squared. All right, so we're trying to find which one, the 15 kilogram mass. So we're trying to find the speed of this one after the collision, which means I want to get rid of v2f. So let's solve this for v2f. So if I put this down here, this is going to be 120 minus 15 times speed 1 final plus 5, plus is equal to 5v2 final. I could divide everything by 5. 120 divided by 5, 24, right? Is 24 minus 3 speed 1 final is equal to speed 2 final. Now I'm going to have to square all this in order to be able to substitute that in here. All right, so when I square this, first inside, outside, last. So 24 times 24 would be 24 squared. Inside would be these two terms. 3 times 24 is 72, minus 72 speed 1 final. But I have to multiply this twice, minus 72 v1 final. And then minus this last term squared, but minus minus plus 9 v1 final squared is equal to v2 final squared. And then negative 72 is negative 144. 24 squared, why can't I remember that off the top of my head? 576 minus 144 speed 1 final minus 72, not 72, minus, did that, plus 9 speed 1 final squared is equal to speed 2 final squared. So I can substitute this in here, and let's put this down here. So I have 960 is equal to 15 final speed of mass 1 squared plus 5. Maybe I should divide by 5 here. Oh, well, whatever. It's all equal to plus 5 times 576 minus 144 speed 1 final plus 9 speed 1 final squared. Let's just divide everything by 5. 960 divided by 5 is 192. 15 divided by 5 is 3. 576 minus 144 speed 1 final plus 9 speed 1 final squared. Combine some like terms. 9 plus 3 is 12. Speed 1 final squared. 576 minus 192. 378. Let's put that in, plus 378. And then I only have 1 with the BF, so minus 144 speed 1 final plus that is all equal to 0. So we have a quadratic. What is 378 divisible by? Not 12, but it should be divisible by 6, right? Yeah. So I could divide everything by 6. Yeah. All right, so 0 is equal to 2 speed 1 final squared minus 24 plus 63. Yeah, it should be. What would be my factor? So, I mean, I have a 63, so like a 7 and a 9 probably. But no, that wouldn't give me my 24. Yeah, 21 and 3. There we go. 21 and 3 is probably going to be it. But that won't give me this. Guess I could just put it in my calculator and have it factor it. That wouldn't be fun. So 2 E1 final, probably a V1 final. And then I have this, what, like probably a 21 and a 3. That'll give me my 63, but no, that's not going to be quite right. 9 and 7 were my other options. 7. No, that's not going to give me an even number either. Oh, well, I'll factor it on my calculator. I can't remember quadratic formula off the top of my head. Give me a second. Negative b plus squared times 2 times 63 divided by 4. Yeah, something went off here somewhere. I feel like I subtracted a number incorrectly somewhere. This is why I should work things out beforehand. Does anyone see my immediate mistake before I just go through and check all of these again? Zero 12 squared. Yeah, that looks a little bit nicer than mine. What did I? 378. Yeah, so 12, 140. Yeah, so this one went off somewhere. Where did that mess up at? 68 divided by 12. No, not divided by 12. Divided by 192. Did I mess up this 576? Where did I get it? Yeah, where did I mess this up to not get 384 then? This came from here. 960 divided by 5, 192. It's really close to what I got. So I'm just going to go with what you got. I don't know where I messed up, but it's going to be something in this. I can't see it immediately, and I'm not going to sit here with it. So I'll take your word for it that you end up getting the 0 is equal to 12v squared minus 144v plus 384. Because, yeah, it should reduce down something nice like that. This number is off 6 somewhere, and I don't see where I messed that number up by 6. But it happened. So, yeah. 12 divided by 12 is obviously 1. 144 divided by 12, 12. 384 divided by 12, don't know off the top of my head. Like you said, is 32. And, yeah, that's a lot nicer of a number to factor. Something that multiplies, but then multiplies to 32. So what? 8 and 4, that makes sense. So -8, -4, minus 8, minus 4. 8 times 4 is 32. No, that's not gonna. Yeah, that'll do it. So -8v, -4v goes to -12v, v squared. So we get v would equal to 8 meters per second, and v equals 4 meters per second. Now, the 15 kilogram mass is initially moving at 8 meters per second. Yeah, or realize only one of those. That's what I was about to get at. So only one of those answer choices.
Ho, ho, ho. Merry Christmas.
Merry Christmas. We realize only one of these is slower than the original, so yeah, it should be 4 meters per second. A. Let's actually see if that's what they got. A. Yeah, that's how we get our answer a lot of times in physics. We get 2 answers. It was originally going 8 meters per second. It obviously slowed down. 205. Yeah, it is A. And yeah, if anyone finds out where I messed up that 378 at. If you subtract 192. What? No, I subtracted 192. I don't know. I just something stupid in there. I just don't see it off the top of my head. If you find where I went wrong, I'll give you some points. Hello. And then yeah, if you're new here, if you want to ask a question, you can turn on your microphone and then ask the question. But while you're not talking, it would be nice if you turn your microphone off. You can turn your video on and your face will pop up if you don't mind, but you don't have to. I don't know. I had plenty of space to write all this, so I'm sure you will too. I'm just kidding. If you need extra space, you can write it on paper. Any other questions? Do I have a schedule for next week? So next week, again, I'm probably going to do AP Monday, dual credit MST Tuesday, AP Wednesday, dual credit MST Thursday, AP again Friday. I'm probably going to have tutorials Tuesday and Thursday in the afternoon. So I'll post that after this. Let's see, schedule. Some of the spring homework. Yeah, I can do some of the spring homework or classwork. Where did I make the mistake at? 7th or 8th line. 576 minus. Oh yeah, I just can't subtract. I put it in my calculator too. Yeah, literally just had to subtract here. There we go. And then that would have been 64. And that is way nicer. And then just ignore that. I'm using my calculator. I don't know how I messed that up. Wait, what else? 147. All right, we'll do 147. Yeah, I'm going to focus on this one for now, and then maybe at about 11, I'll start taking questions about homework and classwork. So hold on to questions about that, just so I don't have to keep scrolling between different things. 147. Which one is 147? Don't trust calculators. That's true. I just haven't been like thinking about as much math in my head recently, so my brain is kind of mush at the moment. All right, refer to the following graph, which represents the hypothetical potential energy curve for a particle of mass m. If the particle is released from rest at position r naught, its speed at position 2 r naught is. If you already turned in the spring homework, you don't mark it as done. If the grade's already in, I'm just going to ignore it. So if it's one of the homeworks that you've already turned in, don't worry about that. All right, so which potential energy am I looking at here? Is this the MGH or the GMM over R? I built a setup that lets me go back and forth. So yeah, we have an inverse relationship. They're not dealing with the negative, so I guess they're calling 0 at the surface of the planet, which is a bit odd. But yeah, we're looking at the GMM over R. At least from position R naught, a speed at 2 R naught is most nearly. Actually, no, I think it looks like they're just using. I think that's what they're doing. 147. So our gravitational potential energy is turning into kinetic energy. And then we still have gravitational potential energy at the end. It actually doesn't matter. Yeah, now that I think about it, it actually doesn't. Now we are going to use the MGH. It doesn't really matter. The curve could just be it's on a ramp as opposed to in free fall. I take back what I said earlier about the GMM over R. So I'm pretty sure this is just on a curve now that I look at it. So we have MGH initial. So we start with potential energy were dropped. So we have no kinetic energy. This is turning into kinetic energy. And we still have some left gravitational potential energy because we don't go to a height of 0. So yeah. Actually, no, we're not. They just have this at U naught. So I should probably just do, instead of MGH, we're just going to be doing 3 U naught, and then we end up at U naught. All right. So I can subtract this. 3 minus 1 is 2 U naught is equal to 1/2 mass times final speed squared. Multiply by 2, so we get 4 times that initial, or U naught, that's not even the initial potential energy, but whatever that gravitational potential energy was, is equal to mass times final speed squared, divide mass. 4 U naught divided by mass is equal to final speed squared. So we're going to take the square root. And so I guess the answer should be C. And then 148, I think they're saying that's part of it. I know it says 16 to 17. I'm pretty sure they mean 147 to 148. So not a conservative force. Again, what does not conservative force mean? And again, you can either type the answer or you can unmute your microphone and say the answer. So heat isn't the actual force, but yeah, anything that's generating heat. So yeah, friction is the non-conservative force. Heat is where the energy goes to make it non-conservative. So yeah, that's going to be friction is not a conservative force. So a non-conservative force depends on the path. So if it cares about your distance taken. A conservative force only cares about your displacement, where you start and where you end. All right. What other questions were there? I saw. Wait, what did Bernie say? Yeah, 82 and 83. 82 and 83. I'll look at 166 after that. Oh wait, this is actually a good one. There's a few things that are real easy to mess up on 82 and 83. All right, so we have a 0.06 kilogram tennis ball moving at 15 meters per second, strikes a tennis racket, and rebounds at 10 meters per second in the opposite direction as shown. The ball is in contact with the racket for 0.030 seconds. And 82 wants us to find the magnitude of average force exerted by the racket on the ball. All right, so how could I get force without using kinematics? Because kinematics is boring. So we are going to be using force as mass times acceleration. We could do force as mass times acceleration. That is a thing we can do. I'm going to choose to do this a different way. There's another way to get force. So we have force, we have time. Yeah, so force times time is change in momentum. That's what I'm going to choose to use. You could use force as mass times acceleration, but it seems like this is more what they were trying to get at. So change in momentum. So we have final momentum minus initial momentum is equal to force times change in time. Now we have to be really careful about direction here. So before we're going in at 15 meters per second, and then after it's hit, it's bouncing back at 10 meters per second. So I'm going to call this final going to the left a negative. So mass, what's the mass of this thing? 0.06 kilograms. Moving to the left at 10 meters per second, minus my initial still 0.06 kilograms. Moving to the right, positive 15 meters per second, is all equal to, we're trying to find that force, and it collides for a time of 0.03 seconds. I just like this because I don't have to use a kinematic equation, get acceleration, and then put that into F equals ma. There's nothing wrong with using kinematics here and then plugging into F equals ma. Just not my preferred method. 0.06. Make sure you do the negative 10. Divided by 0.03. And then they said magnitude of average force. So I'm getting a force of negative 50 newtons, which is just 50 newtons left because I called left negative. And then 83 is just one of these types of questions that they're always going to slip in. How does the magnitude of average force exerted by the ball on the racket compare to the magnitude of the average force exerted by the racket on the ball? And then when you say third law, let's be specific. I know you're just typing it, but whose third law? Yeah, Newton's, because Kepler has some laws. There's like a third law of thermodynamics. So there's a lot of ways. So just when you write it down, put Newton's third law. So yeah, so every reaction, equal and opposite reaction. So the tennis ball hits the racket with an equal force that the racket hits the tennis ball. Just the tennis ball hits the racket to the right. The racket hits the tennis ball to the left. So they're equal magnitudes of forces. All right, what's next? 166. All right, yeah, we haven't really done a question like this. Two identical massless springs are hung from a horizontal support. A block of mass 1.2 kilograms is suspended from the pair of springs as shown. When the block is in equilibrium, each spring is stretched an additional 0.15 meters. When the block is set in oscillation with amplitude A, it passes through its equilibrium point with speed v. In which of the following cases will the block, when oscillating with amplitude A, also have a speed v when it passes through the equilibrium point? All right, so what are some things to think about on this one? So they're identical springs, right? So a page of work for 166. You shouldn't need that much. 166. So when we do this, 1.2 kilograms, what's the weight if we have a mass of 1.2 kilograms? 1.2 times 9.8. So about 11.76 newtons. We'll just say 11.8 newtons. So when I look at this, I could say 11.8 newtons. Each one of these springs is identical, so it should be each holding up half of that. So what, like 5.9 newtons? All right, so if I do this, so if the block is hung from only one of the two springs, then we're going to see this spring has to hold up all 11.8 newtons of force. And so we're going to see that this one is having to pull with a lot more force, and we're going to see it's going to go slower, right? If it's a single spring, it's going to be harder for that spring to move it, so it's going to go a lot slower. That's what my setup is built out of. It's the entire thing is built like this. So I have a thing that can like flip up and down. Yeah, they're a rapid prototyping tool. I actually have a few different ones I've gone through. So I had one that I was trying that kind of worked well, but it had like some rubber bands on here, and it could move back and forth and like snap. But that covered too much of the screen, and so I switched to this model. All right, so we can see here, this one is holding up less of the weight. So this is almost like I have two springs. So I could almost say like if each one has a spring constant K, this one is like it has a spring constant of 2K. The single spring only has a spring constant of K. And then if I have two springs, one spring, and then I have another spring, we're going to see 11.8 newtons. But according to Newton's third law, all of these internal forces are going to be equal to each other. So this one holds up 11.8 newtons. This one holds up 11.8 newtons. So these will both stretch the same amount. So even though these both have a spring constant K, my total spring constant is just going to be K. So this is what they're talking about series when you go through one spring and the other one right after it. Parallels when you have two right next to each other. So in the block itself, from just one of the springs, we're going to see our spring constant changes. So when we're talking about the speed as it travels to the equilibrium, yeah, so I guess we can talk about conservation of energy. So we can talk about, do we even need to go that far? No, yeah, it's also pulled down to the same amplitude A. So yeah, we just need to talk about 1/2 kx squared is going to be turning into kinetic energy, 1/2 mv final squared. Now, for each of these, it's saying it's going to the same amplitude, 1/2 mass times final speed squared. So we're not changing the mass. We're not changing 1/2. So we're seeing which one would have the same final speed. We're keeping the amplitude the same. So that means we're going to have the same spring constant in order for this to go through the equilibrium position with the same speed. So it can't be 1, because if it's held from just one spring, my spring constant is going to be K. when the spring constant was 2K. So that can't be true. So 1 is incorrect. 2, the block is hung from the same 2 springs, but they're connected in series rather than parallel. Again, it's going to be as if it's just one really long spring. Spring constant only depends on the spring itself, not how much of the spring we have. It's kind of like density. Density doesn't care how much of something I have. It'll be the same throughout the material. So it can't be 2 because it's going to be a different spring constant. And then 3, a 0.5 kilogram mass is attached to the block. So when we change the mass, that's going to change the mass here. So that's no longer constant. So yeah, it can't be 3 either. So it should just be none of them. Let me make sure it is none of them. And I'm not doing something stupid. Because that definitely happens. Yeah, it is none of them. Yeah, 166 is none of them. So we haven't talked about this one, so that's why you're struggling with it. But yeah, none of them work. You could do a lot more math, but it's sufficient to just look at kinetic spring potential energy turning into kinetic energy. If I have 2 springs side by side, it's like I have a really strong spring, so I'm going to have a bigger spring constant. A single spring is going to have a smaller spring constant than 2 of them. And then 2 springs in a row, it's just like you have a longer spring that's identical to the other ones. And so it's going to have the same spring constant. And in the end, we would have to have something where either the spring constant changes by the same factor as mass changes, but none of them do. Each one either only changes the spring constant or changes the mass. None isn't usually an answer, which is, it could be very easily. And there is a good chance, I forgot who said it. Was it you, Bernie? So whoever posted that they got the survey from College Board asking if you just wanted to take a 45-minute free response question. So there's a chance you don't even have any multiple choices. So that would be interesting. Any questions on 166 before I move on? Yeah, I know a lot of people prefer multiple choice, but 45 minutes, and I'm assuming what they're probably going to do if they do a 45-minute online one is they're probably going to give you all completely different questions, so it's harder, so you can't ask each other for help, but there's nothing stopping you from cheating. Not that I condone that, but so what I assume is they might just be making a few extra questions, but I'm pretty sure they probably have a lot of spare questions. They normally have a lot of different versions of the test, and so I assume it's not a whole lot of extra work. But yeah, free response questions are easy to make. I can make like a free response question in like a few minutes and then have it fully tested in under an hour to make sure it's like nothing stupid in it. Yeah, I'm not going to actively help you because I could see that being really problematic. They're probably still going to make you sign some sort of honor statement that you're not cheating, and I'm not going to be involved in helping you do that. I am not condoning cheating. I am not saying to cheat, so don't say that I said that. All right, 79. All right. Dart gun is used to fire 2 rubber darts with different but unknown masses, mass 1 and mass 2. The gun exerts the same constant force on each dart, but the magnitude F is unknown. The magnitudes of acceleration of both darts, A1 and A2 respectively, are measured. Which of the following can be determined from these data? All right, so let's see. 2 rubber darts, different unknown masses, same force F, the acceleration R measured. So we know, let's start by writing that out. We know we don't know mass, we don't know force, but we know acceleration. So we can't really get the force if we don't know mass, because net force equals mass times acceleration. If I don't know mass and I don't know net force, that means I can't get my acceleration. I couldn't use this to solve my mass either, because I would need to know that force. The ratio of mass 1 and mass 2. So they have the same constant force. So I could say the force acting on mass 1 is equal to mass 1 times acceleration 1. The force acting on mass 2 is mass 2 times acceleration 2. So I could divide these two by each other, that equation by that equation, right? They're identical forces, so force divided by force is equal to mass 1 times acceleration 1 times mass 2 times acceleration 2. Because they're identical forces, this just goes to 1. And so I could get mass 1 divided by mass 2, multiply A2 divided A1 is equal to the acceleration 2 divided by acceleration 1. I know these accelerations. So because I know these values, that means I could get the ratio of the masses. So I can definitely get C. C is looking pretty likely right now. D, force, and the ratio of mass 1 and mass 2 only. Well, I can't get the ratio, but like we said, we can't get the force, and yeah, we can't get the mass. So I'm thinking C. Let me check and make sure C is the actual answer. Yeah, C. So because we don't know what the force is, we can't get mass. Because we don't know what the mass is, we can't get force. But because we know the forces are identical, we could get a ratio. Because these two terms are identical, when I get the ratio by dividing forces, that goes to 1. And then I'm left over with, I know my accelerations. I have 2 unknown masses, but if I'm looking for a ratio, it's okay to have 2 unknowns. Any other questions on here? 109. All right. If the normal force between two surfaces is double, the static friction force will. Now, this is kind of really funny to me because in here we're going to kind of talk about coefficient of friction just being constant between the two surfaces. As long as the surface is the same, it's constant. But in the real world, sometimes it changes. Sometimes you have more normal force and the coefficient of friction goes up. Sometimes you have more normal force and it actually goes down. So I've seen friction. I've seen AP test question where they accepted all of the answers. Its coefficient of friction was the same, went up or went down as long as the explanation was correct. We're just going to go with the simplified version that coefficient of friction only depends on the two surfaces. So if the normal force is changed, we're going to say the coefficient of friction stays constant. So kind of a simplification. So we're looking at normal force. As long as you're not changing anything, I kind of dislike this question. Whatever. We'll 109. The magnitude of that frictional force is less than or equal to the coefficient of friction times the magnitude of the normal force. Now, it might not actually be equal to this value, but it's always going to be equal to, so the frictional force is going to be equal to some constant times the coefficient of friction times normal force, where this constant is greater than or equal to 0 and less than or equal to 1. So static friction, we're not going to have an equal sign here, but if I multiply it by some number between 0 and 1, I can put the equal sign there. So let's just do that in order to not really stress so much about the less than or equal sign. So the normal force between the surfaces is doubled. We didn't change the surface, so the coefficient of friction is unchanged. I'm assuming we're still pushing with the same force as we were before, but then that wouldn't change. That's the problem I have. That's probably the problem you have with this question. They're not saying anything about pushing it. So if no one is pushing it sideways, then the coefficient of the static friction will be the same. But if they're pushing it with a certain force, the static friction would be the same. But if it's asking how much force is required to move it, the friction. I really dislike this question. That's a terrible question. Let's look at what they were trying to ask. Wait, they're talking about coefficient of friction here. Why are they saying static friction? Is that what it says in the question? Oh, that's what's happening. So on here, so on yours, they're asking the normal force between the two surfaces double the static friction force will, but in the answer key, they're saying the coefficient of static friction. So, yeah, so you kind of have to look at it as the coefficient of static friction. Otherwise, you can't really answer that question. So yeah, the coefficient of static friction will be the same. But we just don't have enough information to answer it about that frictional force. Yeah, I agree. There's too many independent things. If they had said kinetic friction, then so if it was a kinetic friction, that means the object is moving, and then that would mean if you double the normal force, the coefficient of friction remains constant, and then the kinetic friction, would be doubled. So yeah, they could have said kinetic friction and it would have worked, but yeah, just go with that. If it's a question like this, there's probably not going to be one of the ones that I actually scan through to grade. Other questions on here? B. Yeah, they're going for B for coefficient of static friction. Just change the wording on your test and write that in. Any other questions? Or is the take-home test more or less okay? 183. Didn't I do 183 yesterday, or did I not? Or not yesterday, but the day before. Coefficient of friction does not depend on the surface area. It's intrinsic quantity like density is. So density doesn't matter about the volume. So this doesn't matter. It only cares about the surfaces. Oh yeah, 183. Just skip 183. This is a calculus-based question, so you can cross out 183. Yeah, parallel axis theorem. I don't know how much you even get into parallel axis theorem in physics C. You would just integrate about the points. So yeah, you would do mass integral. So dn would be your differential. So cross out 183. Any other questions, or do you want to go on to one of the classworks or the homework? $177. Yeah, 177. That's a good one. Why is rolling? Okay, so rolling friction, we're not going to really deal with rolling friction in here. So rolling friction is a little bit different. It's not actually motion between the two surfaces. Rolling friction occurs when you have something moving and it like contorts, it moves, so it bends. That motion causes internal frictions, and it's that internal friction that causes rolling friction. So if we have a hard surface, there's not going to be any rolling friction, and it's a lot more difficult to account for than sliding friction. So when we're talking about anything rolling across the surface in here, it's still just going to be talking about static or kinetic frictions. So here, the roller rolls without slipping. So if it rolls without slipping, is a static or kinetic friction? So rolls without slipping. So there's no motion directly between the two surfaces. So this is going to be static friction. So even though it's moving, while it moves, the surface doesn't slide. It would have to slip for there to be kinetic friction. But if it rolls, we can actually see that each individual point is going to just kind of, this way might work. So it'll kind of roll and touch the surface without slipping. So it will be static friction. All right, so acceleration of the center of mass. It doesn't say, yeah, uniform cylinder. So uniform cylinder, moment of inertia for a cylinder is going to be 1/2 mr squared. All right, trying to find the acceleration of the center of mass. So that means we're probably going to draw a free body diagram. So we have this. What forces are acting on this object? All right, so friction and F. I'm going to draw this applied force a little bit longer. It doesn't say that that's bigger than the force of friction, but we'll assume it's bigger and it's speeding up. Our frictional force acts from the surface where the cylinder hits the surface. How do you know if there's no friction? So we know there's friction because it rolls. If a thing is being pushed here without friction, it's just going to slide. If it rolls, we're going to see the only force that can make it roll if I'm pushing towards the center is going to be friction. So because when we draw our gravity and normal force, so our gravity points down from the center here, and our normal force is going to go up from the surface through the center of mass. Drew that a little bit too long. our normal force and gravity are going to be equal to each other, flat surface, not accelerating up or down. So the only force that's not acting through the center of the mass is my friction. So I need some force acting away from the center of the object where it rolls, and then it needs to be at some angle that's not towards the center or away from the center. So friction is the only thing here that's actually making this thing roll. All right. So we're trying to find acceleration. So free body diagram, I see normal force and weight balance each other out, but we are accelerating, so we'll have a net force. And our net force is going to be this applied force minus the force of friction. And net force is equal to mass times acceleration. Now, we're not given enough information to solve for frictional force. And even if we wanted to, it's static friction, right? So that means when we do our friction equation, it's going to be force of friction is less than the coefficient of static friction times the normal force. Nothing telling us that we're close to moving. So we can't use that as an equation. It's probably going to be, we're going to need to get rid of our frictional force somehow. So I'm going to add this over and subtract MA. So that applied force minus mass times acceleration is equal to our frictional force. And we're kind of stuck here. I want acceleration. I know mass. Yeah, I'm given mass. I'm given force F, but I don't know my frictional force. Two unknowns. Where am I going to get my other equation for this problem? Torque, exactly. So torque and particularly angular acceleration. So angular acceleration is going to be net torque divided by that moment of inertia. We know our torque is going to be radius times force. Again, which of these four forces is causing our torque? Not F. F is being pushed directly through the center. If I push something directly to the center, it's not going to make it roll. I have to push along the side to make something roll. So what's the only force that's pushing along the side? So force of friction. So friction is going to be the thing that makes it roll. Just imagine if I was pushing this along ice, it wouldn't actually roll, it would slide. All right, so what is friction? It's 90 degrees, so I'm not going to worry about that sine 90. Yeah, I might as well write it. Sine 90 degrees, whatever. Moment of inertia, like we saw for a cylinder, 1/2 mass times radius squared. On the test, if you need this, they will give that to you. All right, we have our equations. The distance is that angular distance times radius. My tangential speed is going to be the angular speed times radius. My tangential acceleration is angular speed times angular acceleration times radius. So we'll see our angular acceleration is that tangential acceleration divided by radius. So tangential acceleration divided by radius. If I divide by 1/2, it's multiplying by 2. Radius, force of friction, sine 90 is just 1. Divided by mass times radius squared. I can multiply radius over, so the acceleration is going to be 2 times radius squared times force of friction divided by mass times radius squared. Radius squared divided by radius squared goes to 1. I know my frictional force here. All right, so the acceleration is going to equal to 2 times force minus mass times acceleration divided by the mass. So acceleration is going to be 2 times the force divided by the mass minus 2 mass divided by mass goes to 1, 2 times acceleration. So I could add 2 acceleration to the other side. So I get 3 times that acceleration is 2 force divided by mass. Or acceleration is 2 times the force divided by 3 times the mass, which looks like C. Yeah. $4D on the spring homework. All right, let's pull it up. I've done quite a few on this take-home test. So yeah, hopefully if you followed along a lot of these, you should have a nice, easy grade for the homeworks. Or for the take-home test, I mean. So I don't actually have any of my keys with me. I didn't know that we were going to be stuck at home. So I'm going to have to be solving these from scratch. So I might make a mistake here or there, as you see when I'm doing something for the first time in a long time. It happens. Oh yeah. This is the one I'm not super concerned about that one. I don't. That one's messy. So I think I said, didn't I say you could skip D and E? Just try to get. Yeah, just try to get F. Yeah, don't worry about D and E. Though I don't think they're gonna ask a question like that in the AP test. I have other things I'd rather worry about. Any other questions? Number 1 on the homework. All of number 1? I guess. Are you more looking at number 1D? Because again, number 1D I assigned as a bonus. So yeah, number 1D you have to get. It's going to be a kind of nasty expression, and you're going to have to use quadratic formula on it. So 1D, again, you're not going to have that difficult of math. Solve that for bonus points, and you don't have to solve it. But to give you an idea, I normally don't take up a lot of space. I filled up this whole area and then some of this area up here to solve it. So not too worried about that one. If there aren't questions by the end, I'm not going to solve 1D, but if there's no more questions other than that, I guess I'll solve 4D for you, but... Didn't we already do 4A? I thought we did 4A. Because we did through C. I could be wrong. I thought we did 4A. Any other questions on anything? Because yeah, I think we did most of these. I forget. Number 6E on the classwork. Yeah, I think I forgot which one I was going to go over when I got back. I think it may have been towards the end of the classwork. Oh yeah. Yeah, I don't know if I finished these. Yeah, we can. Well, I'll go through 6 because I know we've started it. I think I kind of rushed with some of the classes. Yeah, let's do 6. And then this is on the classwork. All right, a 2-kilogram block is dropped from a height of 0.45 meters above an uncompressed spring as shown above. The spring has an elastic constant of 200 newtons per meter and negligible mass. So if the spring doesn't have mass, I know these two things collide and stick together, but is that an inelastic collision if the other object doesn't have mass? So how should we think of that collision if the spring doesn't have mass? Because it is an inelastic collision, they collide and stick together, right? But because the spring doesn't have mass, if we use conservation of momentum, we're going to see that the mass of the spring itself isn't going to slow down the block. So if the block doesn't slow down just from hitting the massless object that is the spring initially, then your energy also won't be lost. So even though this is colliding and sticking together, because it's saying the spring is massless, it's also saying that there's no energy lost, even though it's an inelastic collision. So it's only going to be problematic if they had, say, something right here. There was like a plate with some sort of mass where it collided with the spring, then we would have to use conservation of momentum. But because it's colliding with an object without mass, we're just going to say that energy is going to be conserved. So determine the speed of the block the instant it hits the spring. So again, we did this in class. We have gravitational potential energy is turning into kinetic energy. So mass times acceleration due to gravity times height initial equals 1/2 mass times final speed squared. Like so many times before, mass divides out, multiply by 2, take a square root, 2 times acceleration due to gravity times initial height is equal to final speed squared. Final speed is the square root of 2 times 9.8 times, how high was it? 0.45 meters. And 2.97 meters per second. B wants us to determine the force in the spring when the block reaches equilibrium position. So not when the spring is in equilibrium, but when the block is in equilibrium. So like we saw, the block is in equilibrium. The block, equilibrium, when the forces are balanced. So the block will be in equilibrium when the spring force up is balanced with the weight down. So if we're trying to find the force in the spring, so we're trying to solve for the spring force. So when the block is in equilibrium, the spring force is going to equal the weight of the block. So the block is 2 kilograms times 9.8 meters per second squared. So our spring force is just going to be 19.6 newtons. So again, the block is in equilibrium when the net force on the block is 0. The spring is in equilibrium when their spring is not stretched or compressed. Right? The block is in equilibrium when the net force on the block is 0. The spring is in equilibrium when the spring is not stretched or compressed. All right, so C wants to know the distance the spring is compressed at the equilibrium position. And again, we should kind of change the wording there. This should say at the block equilibrium position. So I want to determine the distance the spring is compressed at the block equilibrium position. So that's just our spring force equation, is spring constant times displacement of the mass of the spring from equilibrium. So I have a 19.6 Newton force. We have a 200 Newton per meter spring force. So the distance in particular, so it doesn't matter about direction, 196 divided by 200, 19.6 divided by 200, 0.098 meters, or somewhere right around 0.1 meters, or 10 centimeters. All right, so D wants us to figure out how fast this block is going. So there's a few ways to look at this. Again, even though there is a collision, because the spring is massless, we're not losing energy from that collision. The spring would have to have a mass, or there would have to be a plate where the spring collided with the mass to be losing energy. So it doesn't really matter where we look at this. Let's look at from the collision will be initial until the block equilibrium will be the final. So our total mechanical energy is going to be conserved. And what types of energies do we have? All right, so we have gravitational potential energy. We have spring potential energy, and we have kinetic energy. Gravitational potential energy final plus spring potential energy final plus kinetic energy final. Now I can go through and call some things 0. Gravitational potential energy, we know our distance the spring compresses, so I'm going to say the initial height is at 0.098 meters, and we'll say our final is that equilibrium position, which we'll say is 0 meters. So I'll say initially I have gravitational potential energy, but we won't have spring potential energy yet because the spring is not compressed yet. And we do have kinetic energy because we are moving. So then when I reach the block equilibrium position, that's where I called 0 height. The spring is compressed and the mass is moving, so I still have both of those at the end. All right, so mass times acceleration due to gravity times initial height plus 1/2 mass times the initial speed squared is all equal to 1/2 spring constant times that final displacement from equilibrium squared plus 1/2 mass times final velocity squared, well, final speed squared, And there's nothing that all of these terms have that I can divide out, unfortunately, so I'm just going to have to substitute all my values. So 2 is the mass, 9.8 meters per second squared is my acceleration due to gravity. We start at a height of 0.098 meters up. This is all going to equal to 1/2. Spring constant is 200 newtons per meter. We compress a distance of 0.098 meters. Plus 1/2. 2 is our mass, and we don't know that final speed. Oh, and I forgot to square this. What happened to... I just forgot it existed. 1/2 times 2 times the initial speed was at 2.97 squared. And yeah, that's what it is. So it should be something like 3.13 meters per second. And then finally, E. I like question E. E is the thing I could see them asking you on the AP test. If you know calculus, this should be a really straightforward question. But for everyone else, it's going to be a little bit more thinking involved. So let's kind of look at different cases. So before the block equilibrium, and then we have at the block equilibrium, and then we have after the block equilibrium. So before block equilibrium, the spring isn't compressed very much. So which force is bigger, our spring force or the weight? So initially, the spring isn't compressed very much. So before we reach block equilibrium, the spring is barely compressed. So big or small spring force? No guesses? So we can draw our force of gravity. This is going to be the same for all of these, right? This isn't changing. So before block equilibrium, spring is barely compressed. So barely compressed, big or small spring force. Not going to write until someone answers. There we go, small. Wait, were those not showing up for me? Oh, I may have just not seen them. Yeah. So barely compressed, we have a small spring force. I guess it wasn't scrolling. Sorry about that. So we have a small spring force. Then when we get to equilibrium, we have a balanced force where a spring force up is equal. And then after equilibrium, the spring is compressed a lot. So when the spring is compressed a lot, we have a it's going to be the other one. Big spring force. There we go. Compressed a lot. We have a big spring force. So here we accelerate down. Here our acceleration is 0. And then here we accelerate up. Let's actually just put this in words. So we accelerate up. And we, not up, we're a big force down. We accelerate down because we have a bigger force down. We accelerate down and we move down. So what's happening to our speed here? If we accelerate down and move down, we speed up. Here our acceleration is 0. So 0 acceleration means constant speed. For that brief moment in time, we have a constant speed there. And then this last one, we accelerate up while moving down. So if we accelerate up while moving down, we're going to slow down. So I could look at this. Before we reach equilibrium, we have a bigger downward force, so we're accelerating down while moving down, so we speed up. At equilibrium, our force is perfectly balanced, so we're not speeding up or slowing down there. And then after equilibrium, the spring starts compressing a lot. I have a really big upwards force, so I have an upward acceleration while I move down, so we're slowing down. So that means equilibrium has to be where we're going fastest. If we go from speeding up to not speeding up to slowing down, that equilibrium position is exactly where this is 0. And you'll solve questions like this in calculus a lot, where you'll go through and you'll be able to see, like, look at derivatives and things like that. Any other questions? Homework, classwork, the college board assignment? Cat? The cat's all the way in the other room. Here, let me see first. camera on the cat for 30 minutes. I can't leave the camera on the cat for that long. When it gets colder, he has this heater that he likes to just sit in front of. The cat's name is Mew, like the Pokemon. What year did we get him?
2016.
2016. Get a new cat, name it Mewtwo. That's a running joke. I don't know. This thing is really needy. So I don't think my wife wants another animal after. His social security number is 123456789. Yeah, he's the only cat I know that actually likes his stomach scratched. I actually don't know what I'm having for lunch.
You should go get something.
My wife wants me to go get something. Toilet paper. No, we actually stocked up on accident. We had just ordered some from Amazon, and then we went to Walmart and we bought some. So we accidentally contributed to the toilet paper crisis. Oh, long enough. What, you just want a 24-hour stream of the cat? I could get a GoPro and just put it on my cat. Wait, I forget. So yeah, the homework and classwork were already passed out in class. So if you see a grade in Skyward, that means you already turned it in. You haven't gotten it back yet, though. Yeah, that's right. You were going to get it back after the break, I think, maybe. So if you don't have it and you have a grade in Skyward, then that's why. Get a bidet. That's the thing. Gamer, I mean, it's just my computer right here. It's nothing crazy about it. I mean, that's my computer, but it's not anything crazy. Extra credit questions. So what I've given for extra credit questions, you can go through and solve questions from the 5 steps to a 5 book. If you work through, try to focus on simple harmonic motion and springs at the moment. But if you do go through and solve some free response questions on there or review questions, write the question out, solve it out, and turn it in. And some of them are even worked out. So even better. So yeah, you can do those for some extra credit. Yeah, the homework and classwork, I don't list it as done because then I'd have to look at it. So yeah, you don't have to list that as done for the homework and classwork if you already have a grade for it. because the grade isn't going from Google Classroom. The grade is going from the. I'm actually putting the grades directly to the Skyward website. And then, yeah, other extra credit questions. I can think of some other extra credit questions, but I don't have any off the top of my head right now. Anything else? There's no other direct questions. I'm going to end the recording now.